welcome. Nice to see so many faces also here on the second day. So I know that many of you know what linear programming is. Yeah, many of you are already experienced with this. The task of these first 45 minutes is, however, to bring us all on the same page and maybe also to see some nice pictures, develop a common language from which we can then start to go into the more technical talks also of Julian, who will give you performance computational talk about how to implement the Simplex method, and Joachim Dahl from Cardinal Operations, who will tell you about the barrier methods and first order methods. Yeah. So for the first lecture here, this is the agenda. So first of all, let's even step one back, go one step back and talk a bit about mathematical optimization. Yeah? LP, IP, MIP. You've already heard something about history, so I'll keep the history short. But and then let's jump into polyhedral theory. Let's look at the feasible regions of linear programs, revisit some duality theory, and from that build up to introduce the simplex method, which is, as we've already heard, one of the most important methods for solving linear programs in practice. And I will only give you a very, very short glimpse on ellipsoid method, barrier and crossover, so you have a more complete picture. All right, so what is mathematical optimization about? Optimization problems consist of variables. Variables is how you describe your actual solution, and of course are related to feasibility. Then you have constraints. Constraints you can evaluate whether they are feasible or violated. And then you have the objective function, which of course tells you how valuable a solution is, what the quality of a solution is. And all this together, if you have a feasible solution with the best possible objective value, you have an optimal solution. That's always our goal. But sometimes it's not easy to directly compute the optimal solution, right? And so we have a very important concept in mathematical optimization, which is the concept of a gap between a dual and a primal bound. So the primal bound is the objective value of the best feasible solution you have found so far. And the dual bound is something that proves you it can't get better, right? In between is the gap. And ideally the gap is zero, so that you have a proof that your primal solution is optimal. Let's look at this in a small toy example. For instance, if you imagine you want to go and find the shortest path from ZIP to TU Berlin. Yeah. So these are slides from the virtual CU at work last time. So and now I want to know, what is the shortest path? Imagine you're a free runner, so you have no restrictions, right? It'll be pretty hard to compute the really shortest path that you can take. But what you can do is you can go on Google Maps and just ask, okay, what's the shortest route by bike, for instance, or by car? And that gives you an 8.07 kilometer driving route. Yeah, that's in some sense a heuristic solution. It's feasible, you could run it, but it addresses a different objective, of course, slightly. And because you might not be allowed actually to run on the Autobahn. But it gives you a dual bound, or you can get a dual bound for your problem by a very simple other way, just looking at the B line. Yeah. And so comparing now the 6.74 with the 8.07 kilometers gives you a difference between the solution that you have and the dual bound that you have, which is 16.48%. Yeah. And in optimization algorithms, then the goal is always to drive this gap to zero. Okay, so let's just formally introduce the optimization problems that we're interested in today and tomorrow. Linear program is consists of a linear function. The feasible for the objective, the feasible set is described by linear constraints, and the variables can take real values. Yeah, often we assume that the variables are non-negative, but they can be free or have some other arbitrary bounds. So all in all, this gives you a convex set of feasible solutions. And we will learn later that there are special solutions which are kind of the corners of this feasible region, which we call basic solutions or vertex solutions, which is a slightly different concept, and we'll get into this. How you write down such a linear program, when you build models, there are very many different forms. So the previous one was just one standard form, but you can convert all of these forms into each other. So if you have a minimization problem, you can make a maximization problem by just multiplying the objective function by -1. If you have an equation, you can get two inequalities out of it, which are equivalent. If you have an inequality, you can turn less than or equal to, you can turn to greater than or equal to. You can also turn an inequality to an equation by just adding a variable. We call this a slack variable, yeah, plus Si. And then the equality here is equivalent to the inequality if we demand that S is 0 or greater, is greater than or equal to 0. Yes, then this is equivalent. And this will actually be an important transformation because in computational standard form used, for instance, for the simplex algorithms, we always want to deal with equality constraints. Yeah. You can also transform unbounded variables to bounded ones, bounded to unbounded variables. All this is possible. So this is the standard form that we often see in LP literature, but actually MIP literature often uses inequalities for the constraints. And also when you model actual problems, you often need inequalities. Okay, so I already mentioned mixed integer programs or MIP. So let's first start with an integer program. This is a linear program where simply the variables must take integral values, yeah? 0, 1, 2, 3, 4. And so the biggest difference between LP and integer program is that the feasible region are now these dots. They are not connected. This is not a convex set anymore. And also it looks easier to solve because we could actually, in theory, enumerate the solutions. This is in practice much harder. Also in theory, much harder, NP hard. Yeah. And now you can, of course, have a mixture where some of the variables are integer and some are real valued. And this is what we call a mixed integer program. And graphically, this would mean that in one direction here, for instance, in x2 direction, we allow real values, while in x1 direction, we only allow integer values. And then the feasible region are these lines here. Yeah. Okay. Good. But this talk is about LP solving. So you've already heard what the first linear program is that was recorded in the literature, the diet problem by George Stiegler. And even before LPs were really around, there were methods around to solve LPs. For instance, the variable elimination method by Fourier from the 19th century. You also heard in the history talk by Professor Grötschel the names of Kantorowicz, who built foundations for linear programming in the USSR, then Danzig, who invented the simplex algorithm, and Lemke and Biel, who came up with the dual simplex algorithm, and then further computational advances later. But we'll get into this later. I want to mention one paper which you've not seen yet, and this is the first paper with an actual computational study on linear programs, yeah, from 1953. So this is a bit after the simplex method was invented, a bit before the dual simplex method actually came up, and this is by Alan Hoffman and co-authors. So in there, they say they discuss three methods which have been employed to solve problems in linear programming, and they compare the results on some special computing hardware. So this is in some sense an interesting point in the literature because, yeah, the literature nowadays is full of computational studies, but back then, of course, there were much less standards established on how to do this properly. So this was very interesting. Okay, and actual commercial implementations came around about the same time, 1954 here, and then more and more stable, 60, 72, the first commercial IP solver. Yeah. All right. but you've had a lot of history yesterday, so let's get into a bit of mathematics. So first of all, let's ask the question, what is actually the set that is described by the feasible solutions of a linear program? And that brings us to Polyhedra. So the nice thing about Polyhedra is, yeah, you can look at all these nice pictures here in 3D, also sometimes appearing in art. And if you want to build Polyhedra yourself, there's a very nice interactive website where you can do this. Yeah. For us, linear programming lives in R to the n, not necessarily R to the 3, but of course we imagine everything in 3D space much more easily. Yeah. And here are some terms that we should distinguish when we think about the feasible regions of linear programs. So a polyhedron formally is defined as the intersection of finitely many half spaces. A half space is described by one linear inequality. And so the intersection of finitely many half spaces means just you have a matrix inequality. Ax less than or equal to b. Each row of this matrix inequality is describes one of your half spaces. And all of this together is the feasible region potentially of your LP. We call it P. Yeah? But now if you look at these pictures, actually the half spaces, these are maybe not the only way to describe actually the feasible region. Of course, very prominent are always also these vertices, right? And so another way how to formally describe an LP is as a polytope. So as the convex hull of finitely many points. So you take these vertex points and then you take the convex combination of all of them, and this gives you also convex set P. Yeah? And now question is, of course, how do these two concepts relate? And first of all, we need a third concept, which is the concept of a polyhedral cone. So going back to the previous picture, all of these polyhedra here were bounded, right? But you can also imagine, for instance, if you look at this tetrahedron here, that this could potentially extend to infinity if you wouldn't have the floor to limit it, right? And then we would talk about a cone, a polyhedral cone, which is described as a conic combination of finitely many rays. Yeah, so simply that's the cone. And now, yeah, the question is, how do all these representations of such objects relate to each other? And there we have the following theorem, which says that a polyhedron has, first of all, this description that we have from the definition, which is the intersection of finitely many half spaces represented as ax less than or equal to b. We can also call this an outer representation, yeah, because kind of we cut away from the space whatever is not feasible, and what is left is the polyhedron. Yeah. But then this theorem tells us that this is such a convex set P is a polyhedron if and only if we also have an inner representation. And that means that we have given a finite set of points here in red and a finite set of rays here in blue. And the region P can be described as the sum of the convex hull of the red points. So this is a polytope, right? That would be a triangle here, plus the cone described by these rays. So here we have actually only one ray, which points in this direction and extends this polytope, this triangle here, into infinity. Yeah? Okay. So that's the formal difference between a polyhedron, a polytope, and a cone. And it will be interesting to think about the outer representation and the inner representation. The outer representation is something that you usually get from modeling, right? Usually you describe your problem by constraints, and constraints are inequalities. The inner representation is much more linked to actually the solutions, right? Because these vertices of the polyhedron, they are solutions, right? And actually what we want in optimization is come from models to solutions. So this becomes an interesting question. Okay, so here are some more nice pictures, special cases of polyhedra or polytopes in this case. And for each of them, we see the two different representations. So here we have the simplex, which has in Rn, n+1 vertices, and is the convex hull of the origin and these unit vectors. Alternatively, I can describe it by the non-negative orthant, x greater than or equal to 0, so x1 greater than or equal to 0, x2 greater than or equal to 0, and so on. And then one inequality, sum of all variables less than or equal to 1. That gives you the simplex. Here you see these two different representations. That would be called a cross polytope. And I'm not sure how clearly you can see it here on the slides. It's essentially the convex hull of all these plus and minus unit vectors, EI. And as a result, you get many more inequalities in order to describe that as a polyhedron. And then, of course, maybe the most well-known polytope is a cube, right? You have 2 to the n points, the convex hull of this, and how many inequalities do you have for each direction? You have 2, so 2n inequalities. Okay, and more generally, just to have the language right, if you had such a polytope or a polyhedron, then we can identify not only the full polyhedron, right, but we can identify different faces which are classified by their dimension. So the vertices are the 0-dimensional faces of the polyhedron. These are what we might also call these corner points. Then the edges are 1-dimensional faces. And on the other end, the most interesting ones are facets, which are just n-1 dimensional faces. So that's, in some sense, the sides of the polyhedron here, if you would call it like that. Okay, but let's get to some algorithmic questions, maybe. Well, algorithms we'll do a bit later, but a mathematical question. So I already told you, when we build a model, we come up with inequalities. We have a polyhedral description, but then of course we want to know, do we actually have a solution for our model, right? So a natural question is to ask, is a polyhedron non-empty? And well, what is the answer if I have given it in the inner representation? So as convex hull of some vertices V plus the cone of some rays E. Is this first polyhedron non-empty? Can you see that already from this abstract description? And why? Yes, yes. So assuming that V is not empty, of course, V are feasible solutions for my problem. V are contained in the polyhedron. Okay, but if I've given it as an inequality system, and this is what I have after modeling usually, then this is actually not trivial, right? So we can't actually tell. It could be either way. How do we answer this? In theory, this question is answered by the Farkas lemma. So the polytope, the Farkas lemma tells you the following. It's empty if and only if I can prove it in the following form. If I can find a combination of these inequalities that are contradictory. So formally, this means I have a vector y of non-negative multipliers, and I form y transposed A. So I sum up, build a weighted sum of the rows of the matrix A to obtain the 0 vector. At the same time, I aggregate the right-hand side, and I obtain something that's negative. Why is this a contradiction? Because if I apply this y to ax less than or equal to b, I get the wrong statement, 0 less than or equal to y transpose b, and that's negative, right? This can't hold. So Farkas lemma tells me the polyhedron is empty if and only if I have such a simple Farkas proof, right? And if it's non-empty, then it's impossible to find that, obviously. And this is kind of a theorem of alternatives. So either it's empty either you have a solution or you have a proof that there is no solution. That's a very nice situation. And this is actually the foundation of all important higher level LP theory, which we'll immediately come to, but maybe just a small example to round this off. So here we have three inequalities. So x1 plus x2 should be together less than or equal to 1/2, say. x1 and x2 at least 1, so this obviously cannot work. So we can transform this first of all in our standard form ax less than or equal to b. And then what does this y mean? Well, this y means I need one multiplier for each row. Can somebody see with which multipliers I need to aggregate the system in order to get my Farkas proof? 1 to 2, yes. So if I add the first and then we see the coefficients all cancel out to 0, but on the right-hand side I get -3. Okay. Good. But yeah, so I already mentioned duality, and so let's move on to a bit more optimization. So here is an example from which we can, I think, see the most important aspects of duality in linear programming. Yeah, so imagine a situation from physics. You have two planes, this violet one and the orange one here, and you have a ball which rests between these two planes. Yeah, this is in some sense an optimization problem. The ball wants to minimize its position, like gravity wants to minimize the position of the ball, but the planes act against it. And essentially, these are linear constraints, right? Maybe it's a bit easier if I add some arrows. So we have an objective function, 0, 1. So 0 times x1 plus 1 times x2, which tries to be minimized. And then the coefficients of this first inequality, 5 and 1, are exactly this vector that points orthogonal to this plane. Yeah? And we want the ball to remain here greater than or equal to 6 to the right of this plane. And here for the orange one, we have -x1 plus 2x2 greater than or equal to 1. Yeah. And now, so if you want to compute the position of the ball, that's easy. You set this to equality, and then you get the position 1, 1 if you just solve this 2x2 system. But how do we now prove that actually the ball cannot be lower? Yeah. How do we do this? Well, in physics, why is this ball stable? Because somehow the two forces that act upon it to the right and to the left top, they act against this objective function. And so our task is a bit like in the Farkas proof to find a conic combination of these two forces to act exactly against the objective function, because otherwise the ball would not be static, right? Can somebody see the multipliers that I need? So with what do I need to scale the violet vector and the orange vector to get the green vector? Somebody? Nine is not correct. 1 and 5 are good. So what I want is a multiplier here and a multiplier here such that these coefficients add up to 0 and these coefficients then add up to 1. Yes, very good, very good. So 5 over 11 for the second and 1 over 11 for the first. And then you see 5 over 11 minus 5 over 11 cancels out to 0. And here we get 11 over 11 is 1. Okay. So this is dual solution to this linear program. This is a proof that the ball cannot be lower. And this I can actually formulate as another linear program, which is called the dual LP. Yeah, and how I do this is that I transpose the problem. So I want to find these multipliers y1, y2, such that the vector 5, 1 times y1 plus the vector minus 1, 2 times y2 gives the objective function 0, 1. These multipliers must be greater than or equal to 0 because I have inequalities. And if I would multiply with something negative, then the sign would change and the meaning would change, right? So, and then basically this force acts against the objective function. So I don't want to minimize, I want to maximize what I get as the aggregated right-hand side, 6 times y1 plus 1 times y2. Okay, this is the dual LP. Very central. And actually the nice thing is on this example here, you can already easily see that the dual LP, if I dualize that again, I get the primal. So which combination of these two dual constraints do I need in order to obtain the dual objective function of 6, 1? 1 and 1, exactly. This is exactly the primal position of the ball, 1 and 1. So in some sense, you see here that the primal is the dual solution of the dual problem. So dualization is very much like transposition in linear algebra. Yeah. Okay. This was just an example, so let's get it right in general. So in general, we have a minimization problem, minimizing C transpose X, AX greater than or equal to B, X greater than or equal to 0. So how do we get the proof of the solution quality? Well, there's an easy case. If I actually have one of the constraints which already underestimates my objective function, then I can use that right-hand side. So if the objective function would be 2x1 plus x2, and one constraint is x1 plus x2 greater than or equal to 3, I know the objective function cannot be less than 3. But of course, in general, that will not work. We need these conic combinations of our constraints. They give, again, valid constraints because, well, it's just scaling by positive numbers and summing up valid inequalities. And so the dual LP is to find this conic combination such that we receive a maximal underestimator for the objective function. So formally, here we take this y, we aggregate the inequality system. We compare it to the right-hand to the objective function because we want an underestimator, and that should be maximized. Yeah. And so this all in all gives the dual LP. Maximize y transpose B such that y transpose A is less than or equal to C, y non-negative. Yeah. Okay. So now what do we know about this primal and dual LP? Well, first of all, if you have to do this yourself, right, that might sometimes happen that you actually want to write down the dual LP. This is now here for this standard form, but if you compare, then you already see what you need to do. So here it's summarized again on this slide. So the constraint in the primal LP is a variable in the dual. The variable in the primal becomes a constraint in the dual. Objective direction is inversed, signs are inversed, and so by this scheme also it's easy to see that the dual of the dual is again the primal. Yeah. Okay, but now what do we know about this pair of optimization problems? The first thing is weak duality. Yeah, this means that the optimal value of the dual LP is an underestimator to the optimal value of the primal LP. And this is actually rather simple to prove. This is how we derived it actually, right? Just by using aggregation. Yeah? Y transpose B less than or equal to Y transpose AX. Then you switch the brackets and Y transpose A is less than or equal to C. And so you have that the primal objective can never be smaller than the dual objective. Yeah? This has even made it to Twitter by our esteemed speaker from Thursday, Marco Lübbecke, who will then tell you something about column generation, which is also needs some LP theory. Okay, but it's not only weak duality that holds, we actually have equality. So we call that strong duality. That's the most important and influential theorem in optimization. So the primal has a finite optimum if and only if the dual has a finite optimum and the values are equal. So this is called a min-max result, and in optimization, there are many other min-max results. The proof is not as short as the one for the weak duality. Okay, and so maybe good to think which cases can actually happen for these primal and dual LP. So I already said, if the case where there's a finite optimum, in this case they are the same, but we know that LPs can also be infeasible, right? We've already seen an example before on the slide with the Farkas lemma, and so these other kind of combinations of primal and dual statuses would be that one problem is unbounded and the other one is infeasible. But it can actually also happen that both problems are infeasible. Okay. Another important concept that relates these two problems is complementary slackness. So, and maybe to motivate this a bit, let's look at this picture here. Here we have the optimal solution at one uniquely determined vertex. And actually, if you think about it, the proof of optimality should not involve what happens here at the back of the feasible region, right? Doesn't at all matter what's going on here. All that matters is really what's going on locally around the optimal solution. So in some sense, the proof of optimality should only involve the two inequalities here, which are tight at the optimal solution. And what's the proof? That is the dual solution Y. And so this should mean that the dual multipliers Y are actually 0 for all these non-tight constraints, and only for these tight constraints here, they should be non-zero. And so let's put this a bit more formally. So if I have an pair, an optimal solution pair XY, so a primal dual solution, then I know that for all constraints, it holds that either the multiplier is 0, or if it's not 0, then actually the constraint must be tight. So if I have now a non-zero multiplier here, for instance, this means that actually the inequality here must hold with equality in the optimal solution, which is the case. The optimal solution is exactly on this line. Yeah? And I can also put this for variable bound constraints. So if a variable x greater than or equal to 0, then it's either at the bound 0, or in the dual problem, the dual constraint is tight. Yeah? So this is kind of a primal in a dual slackness condition. Okay, and this is actually also, again, easy to prove by weak duality, because if you look at, this was the proof of weak duality. Now, at an optimal solution pair, this should be an equality, right? Y transpose B should be C transpose X. But you can think about it if this is violated up here. So if Yi is positive and the slack here is also positive, then you will actually get a strict inequality here. And so weak duality would be violated. So complementary slackness is a direct consequence of weak duality. And so the nice thing is, to construct an optimality proof, we can only use local information around the optimal point for the linear program now. There holds even something like strong complementary slackness. So this is only a one-way street here, in some sense, that says that if it's positive, then the constraint must be tight, but you can always create actually a solution where this is an equivalence. So if it's tight, then it's positive. Yeah? Another thing, you can use dual information also for sensitivity analysis. So the dual variables have an interpretation as shadow prices. So in some sense, they tell you how much would the objective function change if you relaxed or tightened this constraint. And maybe let's look at this again here on this slide. So what does relaxing mean? So imagine that this violet line here would be relaxed. That would mean that the 6 would be decreased. right? Then the question of sensitivity analysis is how quickly would this ball move downwards? How quickly would the objective function decrease? And the rate at which this happens is given by the dual multiplier 1/11. Yeah, and the rate at which this happens, if I relax the orange line, is given by 5/11. And there also you see, of course, so if you relax this orange one, the ball will drop much quicker than if you relax the violet one. And this also is reflected into the ordering of the values of the dual variables. Yeah? So how large a dual value is can tell you something about how important this constraint is, how restrictive it is. Okay. Now to repeat some of the things, here are 3 questions. So maybe think about them quickly. If a dual variable has a non-zero value, then which of these 3 statements is correct? The third one? Yes. Then how is this form called to describe a polyhedron? Standard form, outer, inner? Yes, that was the outer representation. And this is a bit more tricky. So what is the dual of the following problem? So this is the standard computational form that also Julian will use in his talk for describing the simplex algorithm, ax equals b, x greater than or equal to 0. The third? Yes. So because we have equality constraints, the dual variables must be free. This is a bit different than what I had in the example. And because of the non-negativity here, the dual constraints are inequalities, and the min must be max. All right, great. Thank you. Okay, then I have 5 more minutes to tell you a bit about algorithms and introduce what then Julian will continue in more detail with the simplex method. First of all, you've already heard the method of Fourier rediscovered by Motzkin, which is basically successive projection of a polyhedron onto an n-1 dimensional space, so eliminating one variable. This is useful to, in theory, it can also be used, for instance, to prove the Farkas lemma. It can also be used, or say maybe abused, for solving a linear program. And so to check also whether polyhedron is empty. It can also be used to transform the inner to the outer representation. That's maybe interesting. Here you see how this works. So if I've given an inner representation, so a list of vertices V and rays E, how do I derive the outer representation? Well, first of all, I write explicitly what I want. So all the x's are convex combinations of these V's and conic combinations of the E's. And then I have these auxiliary variables Y and Z. And Fourier-Motzkin elimination simply helps me to get rid of these Y, Z variables and represent everything in the X space, which will then just be the outer representation. Yeah. So, and this is actually not, this is a hard problem, and Fourier-Motzkin elimination is actually one of the best methods to do this. No? Okay, but then we have to come to more practical methods. So I'm sure you all have heard of the simplex method. So the idea is very intuitive. You start at a random vertex, which is feasible. You look at your neighboring vertices. If you find one which improving objective, you move there. If you realize you can move into infinity, you have an unbounded problem. And if you can't move any further, if you can't do any further local moves, then you are optimal. So this works essentially because the problem is convex. So an optimal boundary solution always exists. And because of linearity, it's also the case that actually always an optimal vertex solution exists. And then because of convexity, local optimality is global optimality. Yeah? So this is the abstract idea why this is correct. But to get a bit more into computations, let's switch the representation into this AX equals B form. And you've already in the question answered what the dual LP for this is. This is easy by introducing slack variables. And also, if this is a feasible LP, then you always have vertices. So what is this actually? You have to imagine this AX equals B as, well, an affine subspace. So for instance, a plane in R3 or a line in R3. And then this is intersected with a non-negative orthant. So you might get this shape, or you might get such a line segment or an unbounded ray. Or of course, in higher dimensional objects, much more difficult things that we cannot imagine. Now, geometrically, it's very clear to us what a vertex is, but of course, the computer does not have a geometrical way of working with things, so he needs linear algebra. And so the important concept for implementing the simplex idea in computer is the concept of basic solutions. And how do I now compute and represent a vertex? So for every vertex, if I look at this AX equals B system, I can single out M by M submatrix B, which can have positive values. All the remaining variables are set to 0. And then I have a linear system of equations, B times X. I use subscript B here with a little bit of abuse of notation to say that I only want the columns contained in this submatrix. So BXB is right-hand side B, and then if I do the inverse, this is the formula I get. All the non-basic variables are set to 0. And so now, this already makes clear that LP is in some sense a discrete optimization task. How many possible bases can I have? M out of N. So these are finitely many. I could enumerate them. Of course, that is not efficient. Now, are these all actually vertices? Well, only if they are really feasible, right? So what does feasibility mean here? Yes, so X must be non-negative. So the AX equals B is expressed here, but a non-negative not. And so, of course, I know that the non-basic variables are all 0, so only the basic ones must be non-negative. Okay, so this is the linear algebra behind primal basic solutions. But of course, from this basis matrix, you can also derive a dual solution, which looks like this. So you can simply ignore the set of the non-basic variables and try to find a y such that y transpose A equals the objective function on these subcolumns. And then you get a dual solution. Yeah? And well, optimality means now what? Yeah, so somehow this y must be dual feasible, right? So it is feasible on the subcolumns of B, but not necessarily on N. And so I need to basically have this dual feasibility constraint here with my y that is computed from the basis matrix. And that is the formula that many of you may have seen already as reduced costs. So the reduced costs here must be non-negative if the basis should be optimal. This is just a rewrite of the dual feasibility. Okay. And so now here's a quick summary of the primal simplex algorithm. So we, first of all, we start with a feasible vertex. We check optimality, which is dual feasibility. Then if not, you increase one variable which has positive reduced cost from 0 to some value delta. And then you need to compute how far you can actually do this until you reach another vertex. And it turns out that the formulas look like this. So you need to also multiply the column of this non-basic variable with the basis inverse. And that gives you kind of a direction here in which you move in the polytope. And then you can see which of the inequalities are stopping you. And this basically gives you another row of your constraint matrix. And that gives you another variable of in your basis. And then you can exchange these. I'm going over this now a bit quickly. Julian will repeat this. Okay, and so here you see the formulas for how to move along the vertices. Okay, so I already mentioned why this is correct. Let's skip over this. Let's just mention one important concept in LP, and that is degeneracy. So the simplex works very nicely if at each step you can make an improving move, and that means if the primal and the dual solutions are unique. Yeah, but it can happen that actually such a vertex solution is not only defined by n hyperplanes, but by many more. Like many more of them could be tied at a solution. That is what is called primal degeneracy, if a vertex is overdefined. But the same thing can also happen in the dual LP, which means that you have many multiple solutions because your objective function is parallel to a face of your feasible region, right? And this you have to deal with in implementations and both in LP solvers and MIP solvers. And yeah, so now I already told you the simplex actually works with basic solutions, and the primal simplex goes through primal feasible basis to reach an optimal, which is a dual feasible basis. But of course, you can do exactly the other thing with the dual simplex. So you can start with a dual feasible basis and pivot through dual feasible basis until you are primal feasible. And then you're also optimal because you have an optimal primal dual solution pair. And theoretically, this is actually nothing else but applying the primal simplex on the dual, but practically it's much more efficient to implement. Yes. And important is that you can also re-optimize with primal and dual simplex in different cases when you change your LP. This you will see in branch and bound will be very important. Let's just quickly think about this. So suppose you have reached an optimal basic solution. So you are primal feasible and dual feasible, and then you change something. For instance, you change the objective. In this case, of course, the basis stays primal feasible. So you can simply continue with the primal simplex, right? You don't have to start from scratch. You can just optimize on. The same holds if you actually add another decision variable to your problem and set it to 0. It doesn't affect primal feasibility. And on the other hand, if you add a new inequality that restricts your feasible region, then, well, of course, primal feasibility is violated. But if you look at the linear algebra, the basis actually stays dual feasible. And so you can use the dual simplex to re-optimize. So it's really important to have both of them. And the same holds if you change the right-hand side or a variable bound. Okay. And so, yes, here are, as I told you, I wanted to give you a few slides on the ellipsoid method and the barrier method, but I will skip over this and stop here because you will see this in Joachim's talk as well on the barrier method. And I don't want to take more time from Julian to introduce you to the computation aspects of the simplex algorithm.